Welcome to No Human Left Behind, AI the podcast. In today's episode, a conversation on machine learning, fundamentals and applications.
Welcome back to the deep dive. Looks like someone's been hitting the books hard on machine learning. We got a whole stack of material from you this time.
You're not kidding.
Gearing up for something big. Maybe for presentation? Or even a job interview on AI.
Could be. You never know what people are prepping for these days.
Well, whatever it is, we're here to make sure you absolutely crush it.
That's right. We'll get you sounding like the AI expert in the room.
So before we get lost in all the algorithms and data, let's take a step back. What exactly is machine learning? I mean, it's not just your typical computer programming, is it?
Definitely not. It's a whole different way of thinking about how computers can solve problems.
Okay, I'm intrigued.
See, in traditional programming, we give the computer very specific instructions, like a step-by-step recipe.
Right. But in machine learning,
It's more like we're giving the computer a bunch of examples and letting it figure out the rules on its own.
So kind of like teaching a kid to ride a bike. You don't give them a manual, you just let them try and fall a few times.
Exactly. It's all about learning from experience, just like humans do.
So instead of rigid rules, these machine learning algorithms are constantly adapting and changing.
That's the beauty of it. They're dynamic, always adjusting based on the data they're processing.
Fascinating. So tell me, how many different flavors of machine learning are out there? The stuff you sent mentioned a few.
Well, there are three main categories. You've got supervised learning, unsupervised learning, and reinforcement learning.
Okay, let's break those down. What's supervised learning all about?
In supervised learning, it's like having a teacher guiding the way. We give the algorithm labeled data, which basically means each input has a corresponding output.
So like flashcards,
Yeah.
with questions on one side and answers on the other.
Perfect analogy. The algorithm learns from these examples and then tries to predict the right output for new, unseen inputs.
I see. So like a spam filter. It's been trained on tons of emails that are labeled as spam or not spam.
Exactly. That's a classic example of supervised learning in action.
Got it. So what about unsupervised learning? Is that like showing up to school but skipping class?
Huh. In a way, yeah. In unsupervised learning, we don't give the algorithm any labeled data. It has to find patterns and relationships all on its own.
Wow, that sounds like a tough job.
It is. Imagine being given a giant jigsaw puzzle with no picture on the box. You'd have to figure out how all the pieces fit together.
So what kind of things can unsupervised learning actually do?
Well, one common task is clustering, where the algorithm groups similar data points together.
Okay, I can see how that would be useful, like grouping customers with similar buying habits.
Exactly. Another important application is anomaly detection.
Anomaly detection.
Yeah, finding those data points that are way different from everything else. Think credit card fraud detection.
Makes sense. So we've got the teacher in supervised learning and the lone wolf in unsupervised learning. What about reinforcement learning? Does that involve, like, sending the algorithm to boot camp?
Haha, not quite. Think of it more like training a pet. We give the algorithm rewards for good behavior and penalties for bad behavior.
You mean like giving it treats or putting it in timeout?
You got it. It learns through trial and error to maximize those rewards.
Interesting. So are we talking about teaching computers to play fetch?
Not exactly, but those game-playing AIs that beat humans at chess, that's reinforcement learning.
Oh, wow. That's pretty impressive.
The algorithm learns by playing millions of games and figuring out which moves lead to wins.
That's wild. So we've got three different approaches to learning, all leading to some pretty amazing outcomes. But what does the actual machine learning process look like? I mean, how do we go from raw data to a working model?
It's a journey, not a destination. It involves a series of steps and lots of refining along the way.
I'm all ears. What's step one?
Data. You can't build a house without bricks, right?
So garbage in, garbage out.
100%. High-quality data is the foundation of any good machine learning model.
Okay, so we've got our data. What's next?
Well, even the best ingredients need some prep work. You gotta clean and pre-process that data.
You mean like getting rid of duplicates, handling missing values, making sure it's all formatted correctly?
Yep, all the boring but essential stuff.
Got it. So what happens after the data is all prepped and ready to go?
Then it's time for feature engineering. This is
Okay.
where human expertise really comes into play.
Feature engineering?
Yeah, it's like choosing the best ingredients for your recipe. You gotta understand which features are most important for the problem you're trying to solve.
So it's not just about feeding the algorithm any data, it's about feeding it the right data.
Absolutely. You want to make sure the algorithm is learning from the most relevant information.
Okay, I'm starting to see the bigger picture here. What comes after feature engineering?
Model selection. You've got to choose the right algorithm for the job.
Ah, so like picking the right tool from a toolbox.
Exactly. There are tons of algorithms out there, each with its own strengths and weaknesses.
So how do you decide which one to use?
It depends on the type of data you have, the kind of problem you're trying to solve, and a bunch of other factors.
Sounds complicated.
It can be, but that's where experience and expertise really come in handy.
Makes sense. Okay, so we've chosen our algorithm. What's next?
Time to train the model. We feed the data to the algorithm and let it learn those patterns.
So it's like sending our student to class and hoping they absorb all the information.
Exactly. This can take a while, especially if you have a massive amount of data.
I bet. So the model's been trained. How do we know if it's actually learned anything?
Time for a pop quiz. We evaluate the model's performance on a separate data set that it's never seen before.
So it's like checking if the student can apply what they've learned to new problems.
Precisely. If the model does well, great. If not, well, back to the drawing board. Maybe tweak some parameters, try a different algorithm, or even gather more data.
It's a continuous process of improvement.
Exactly. And finally, once we're happy with the model's performance, we deploy it into the real world to do its thing.
That's when it gets to shine. But you mentioned earlier that there are tons of different algorithms to choose from. Can we dive into a few of those, especially the ones in the materials you sent? Let's start with supervised learning algorithms.
Sure. Which one catches your eye first?
Let's talk about linear regression. What's the deal with that?
It's a classic. Think of it like trying to find the best fitting line through a bunch of data points.
I vaguely remember that from high school math.
It's simple, but surprisingly powerful,
Yeah.
especially when you have multiple variables to consider.
Okay, give me a real-world example.
Sure, like predicting house prices. You can use linear regression to figure out the relationship between house size, location, and price.
So the bigger the house and the better the location, the higher the price.
Exactly. Linear regression can capture those kinds of relationships.
Interesting. What about logistic regression? The notes say it's actually used for classification, not regression. That seems a bit confusing.
It is a bit of a head-scratcher, but think of logistic regression like a light switch, either on or off. It predicts the probability of something belonging to a specific category.
Okay. So instead of predicting a specific number, it's predicting whether something is more likely to happen or not.
You got it. Like predicting whether a customer will click on an ad based on their browsing history.
That makes sense. Okay. Now, for something that sounds a bit more complex, what about support vector machines, or SVMs?
Ah, yes. Those are a bit more technical, but still very cool.
Can you break them down for me?
Imagine you're trying to draw a line to separate two groups of data points. SVMs aim to find the line that creates the biggest gap between the two groups.
So it's like establishing a clear boundary between two countries on a map.
Perfect analogy, and what makes them really powerful is something called the kernel trick.
The kernel trick.
It allows SVMs to handle even nonlinear data by transforming it into a higher dimensional space. It's like taking a tangled mess of yarn and untangling it by adding another dimension.
Okay, that sounds pretty abstract. Let's move on to something a bit more intuitive. What about decision trees?
Ah, those are fun. Decision trees are like those choose-your-own-adventure books. You start at the top and work your way down, making decisions at each step.
Okay, I can see how that would work with data. You ask a series of questions, and each answer leads you down a different path.
Exactly. It's like playing a game of 20 questions with your data until you finally reach the answer.
And what about random forests? Is that just a bunch of decision trees hanging out together?
More like a whole team of experts pooling their knowledge. It combines multiple decision trees to make a more robust prediction.
So, like getting a second opinion from several doctors.
Precisely. It reduces the risk of overfitting to the training data and makes the model more reliable. We've covered a lot of ground on supervised learning algorithms. Ready to explore the world of unsupervised learning?
Absolutely. Let's dive in. What about this K-means clustering thing? That sounds intriguing.
Okay, so imagine you have a bunch of data points, right? And you want to group them together based on how similar they are.
Okay, I'm following.
So K-means finds these things called centroids, which are kind of like the centers of each group.
So it's like finding the perfect spot to put a snack table at a party so everyone in that group can easily reach it.
Exactly. And the algorithm keeps adjusting those centroids until it finds the best possible grouping where everyone's happy.
I like it. But how does it know how many groups to make in the first place?
That's where the K comes in. You actually have to tell the algorithm how many clusters you want. There are ways to figure out the best number, but that's a whole other conversation.
Okay, so we're basically telling the algorithm, hey, divide these data points into k-groups and make them as tight-knit as possible.
Precisely. Now, if you want to get a little fancier, we can talk about hierarchical clustering.
Ooh, fancy. What's that all about?
Think of it like building a family tree, but for data points.
Okay, I'm picturing a giant tree with branches and leaves, and each leaf is a data point.
You got it. It starts with broad categories and then keeps branching out into more specific subcategories, like organizing a library. You've got fiction and nonfiction. Then within those, you have mystery, romance, history, and so on.
So instead of just grouping things into flat clusters, it's creating a more layered hierarchical structure.
Exactly. It helps you see the relationships between different data points more clearly. Now, ready to step it up a notch?
Hit me with it.
Let's talk about principal component analysis, or PCA for short. It sounds intimidating, but the idea is actually pretty simple.
Okay, I'm listening.
Imagine you have this data set with a ton of variables, right? And some of them might be correlated or redundant. PCA helps you simplify that mess.
So it's like taking a long, rambling speech and condensing it into a short, impactful message without losing the key points.
Perfect analogy. It finds these new variables called principal components that capture most of the important information in a much smaller package.
And this helps with
all sorts of things. Visualizing the data, reducing computational costs, even making other machine learning algorithms work better. It's a real workhorse.
wow, that's pretty powerful stuff. It's amazing how these unsupervised learning techniques can uncover hidden patterns and structure in data. It's like they're revealing secrets that were right there all along.
Exactly. Oh, one more technique I should mention, TSNE. It's great for visualizing high-dimensional data in a way that's easier for our human brains to grasp.
So like taking a complex 3D object and projecting it onto a 2D surface so we can see it better.
Exactly. It tries to keep similar points close together while spreading out dissimilar points. It's really helpful for understanding relationships in complex data sets. We've talked about supervised and unsupervised learning algorithms, but what about reinforcement learning? Ready to circle back to that?
Absolutely. We talked about rewarding good behavior, but I'm still a little fuzzy on how it actually works in practice.
Okay, so picture this. We're teaching a robot to navigate a maze, right? The robot is our agent, and the maze is the environment. Now, the robot's goal is to find the shortest path from the start to the finish. At each step, it observes its current state, which is basically where it is in the maze.
So it's looking around and figuring out its surroundings.
Exactly. And based on that information, it chooses an action, like moving forward, turning left, or turning right.
Okay, I'm seeing the decision-making process here.
Now, here comes the reinforcement part. After each action, the robot receives a reward. If it gets closer to the finish line, it gets a positive reward. If it hits a wall or goes in the wrong direction, it gets a penalty.
So it's like a little kid learning to walk. If they take a step forward, they get praise. If they fall, they get a little scolding.
Exactly. And over time, the robot learns a policy, which is basically a strategy for choosing actions in each state that helps it maximize those rewards and reach the finish line as quickly as possible.
So it's constantly experimenting and learning from its mistakes.
Precisely. There are different algorithms for achieving this, but two of the most popular are Q-learning and SARSA.
I vaguely remember those names from the materials I sent.
Q-learning basically keeps track of which actions lead to good outcomes in each state. It's like the robot is building a mental map of the maze, where each location is associated with the best possible action to take from there.
So it's learning from experience and updating its strategy based on the feedback it receives.
You got it. Now, SARSA is similar, but it also takes into account the current policy the robot is following, which can lead to slightly different learning outcomes.
That's a bit nuanced. Can you elaborate a bit more?
Sure. Imagine the robot is currently following a policy that makes it turn left at every intersection, even if that's not always the best choice. SARSA will learn the values of actions based on this specific policy, while Q-learning will still aim for the optimal policy, regardless of what the robot is currently doing.
Okay, I think I'm starting to see the difference. So SARSA is more focused on evaluating the current strategy, while Q-learning is more focused on finding the absolute best strategy, even if it means deviating from the current one.
Exactly. It's a subtle but important distinction. Reinforcement learning is really fascinating, isn't it? It's like watching a machine learn and adapt in real time.
It is. But as we're getting deeper into this world of machine learning, it's making me think about the bigger picture. It's not just about building cool algorithms, right? There's a whole ethical dimension to consider as well.
Couldn't agree more. It's not enough for these models to be smart, they also need to be ethical. And that brings us to an absolutely critical aspect of machine learning, building models that are both intelligent and responsible.
I'm all ears. What does it take to create a machine learning model that's both smart and ethical?
Well, let's start with smart. A truly smart model goes beyond just fitting the data it's been given. It needs to generalize well to new, unseen data. Remember the overfitting problem we talked about earlier?
Yeah, where the model memorizes the training data instead of actually learning the underlying patterns, like that student who crams for a test but can't apply the concepts in real life.
Exactly. A smart model avoids those pitfalls. It uses techniques like regularization to prevent itself from becoming too specialized to the training data and ensures it can handle new information effectively. Now, let's talk about the ethical part. It's crucial because machine learning is increasingly being used in ways that impact people's lives. We need to make sure these systems are fair, unbiased, and transparent.
Can you give me some examples of how ethical considerations come into play?
Sure, think about a loan approval system, right? If the data used to train that system reflects historical biases and lending practices, guess what? The model might end up perpetuating those biases.
So even if the algorithm itself is neutral, the data it's trained on can introduce bias and lead to unfair outcomes.
Exactly. It's like baking a cake with spoiled ingredients. No matter how good your recipe is, the cake's going to taste bad. We need to be incredibly careful about the data we use and be aware of potential biases that might be lurking within it. Another big ethical concern is transparency. It's about understanding how a model reached a particular decision, especially when it's being used for things like healthcare or criminal justice.
So it's not enough for a model to just spit out an answer. We need to know why it arrived at that answer.
Precisely. If we can't understand the reasoning behind a model's decision, it's hard to trust it. And then there's accountability. Who's responsible when a machine learning system makes a mistake or causes harm? That can get pretty complicated.
I can imagine. These systems can be really complex, and it's not always clear who should be held accountable when things go wrong.
Exactly. As machine learning becomes more intertwined with our lives, we need to establish clear guidelines and frameworks for accountability to ensure these powerful tools are used safely and ethically. Now let's shift gears and talk about the practical side of things, the stuff that actually lets us build these smart and ethical machine learning models.
Okay, let's get into the nuts and bolts. The material I sent you mentioned some popular libraries and frameworks like scikit-learn and TensorFlow. Can you tell me more about them? Those sound like some pretty heavy-duty tools. What are the key differences between them, and are there any other tools that pros use out there?
So scikit-learn is a great place to start, especially if you're new to all this.
Okay, what's so special about it?
Well, it's a Python library, super user-friendly. It's got a whole bunch of algorithms for all sorts of tasks.
Like what? Give me some examples.
You name it. Classification, regression, clustering, you name it. Plus, the documentation is amazing, really easy to follow.
So it's like a one-stop shop for all your machine learning needs.
You could say that. Now, if you're venturing into deep learning territory, TensorFlow is the big player.
Deep learning, that's where things get really interesting, right?
Definitely. Think complex neural networks. TensorFlow is Google's baby, and it's a beast. It can handle some seriously heavy lifting.
Like what kind of stuff?
Image recognition, natural language processing, machine translation, you name it. It's built for those really complex tasks.
TensorFlow sounds pretty impressive. What about PyTorch? I saw that mentioned in the material too.
PyTorch is Facebook's contender, and it's gaining popularity fast.
How does it stack up against TensorFlow?
Well, it's known for being super flexible and easy to use, especially for research. Lots of folks prefer it for its dynamic computation graph, which makes it easier to debug and experiment with.
So it's kind of like choosing between a powerful sports car and a versatile off-road vehicle.
I like that analogy. Both can get you there, but they have different strengths. It all comes down to what you need it for, your own comfort level, and what resources you have available. And hey, if you don't want to set up your own whole computing environment, there's always the cloud.
The cloud. How does that fit into all this?
Cloud platforms like Amazon Web Services, Google Cloud, Microsoft Azure, they all offer machine learning services that are incredibly powerful and scalable.
So you can basically tap into their massive computing power and expertise without having to build everything from scratch.
Exactly. It's like having a whole team of expert chefs and a fully equipped kitchen at your disposal. They provide pre-trained models, tools for building your own models, and all the computing power you could ever need.
Pretty amazing, Reddy.
It is. It seems like machine learning is becoming more accessible every day.
It really is. The tools are getting better, The resources are more readily available, and the possibilities are endless. Speaking of possibilities, I'm curious to hear your thoughts on what the future holds for machine learning. Well, it's clear that machine learning has the power to solve some really big problems, but I'm also aware of the potential risks and challenges.
Absolutely. It's a double-edged sword. As this technology gets more sophisticated and integrated into our lives, we need to be extra careful about how we develop and use it.
You talked about the importance of fairness, transparency, and accountability in machine learning. How do you see those principles shaping the future of AI?
I think we're going to see a bigger push for what's called human-centered AI. It's not just about building smart machines for the sake of being smart. It's about aligning those machines with human values and goals.
I love that idea. It's not about replacing humans, it's about empowering them.
That's it. Giving people the tools they need to tackle complex challenges and make better decisions. It's about creating a future where AI is used to enhance our lives, not disrupt them.
Well said. This whole deep dive has been incredibly insightful. It's amazing to see how far machine learning has come, and the potential it has to shape the future is truly mind-blowing.
It's been a pleasure exploring this fascinating world with you. And remember, this is just the tip of the iceberg. The world of machine learning is vast and constantly evolving.
Absolutely. To our listener out there, we hope this deep dive into machine learning has been illuminating. You've now got a solid grasp of the core concepts, the different types of learning, the ethical considerations, and even some of the tools and technologies that are driving this field forward. So go out there and keep learning, keep exploring, and who knows, maybe you'll be the one making the next big breakthrough in AI.